now going to explain an interesting algorithm which is not very difficult, but which is necessary to know. The longest strictly increasing subsequence problem. So we're given a sequence of numbers in an array. These could be integers or floating point numbers or any other kind of object that could be ordered. And then we want to find a subsequence which is strictly increasing. Like we can go 2, 5, 6, but we can't go 2, 5, 5. All right, now here, for example, in this particular sequence, 2, 5, 1, 8, 6, 9, 4, 7, 3, 8, 4, the longest strictly increasing subsequence is 2, 5, 6, 7, 8. All right, now we're going to build some data structures, and actually they'll all be relatively simple arrays and individual numbers. But if you notice that I have a fictitious member of the sequence, 0, which in position 0, which is minus infinity. Now the array indices here are, I'm going to make them from 1 to n, and then I'll also have 0 here with the fictitious number minus infinity. We don't actually need to have that in the array. But we want every number to have a back pointer, every entry. And so the back pointer of 1 will be 0, the back pointer of 2 will be 1, the back pointer of 3 will be 0. So notice I'm defining the back pointers in terms of the indices rather than the values. So for example, if this is my array here for the back pointers, the numbers I put in here, I don't actually need this one, would be 0, 1, 0, 2, and 6 points to 5, so it's also a 2, and then position 6 has a 9, which points to 6, so that's 3. Position 7 has a 4, which points to 1, which is in position 3. And then, no, this is not 3, this is 5. I'm so sorry. Let me fix that. This is a 5 here, I mistook that. So the 9 points to 6, so that means that in position 4 we have a 9 which points to position 5. And then 7 points to 6, which is also in position 5. 3 points to 1, which is in position 3. And 8 points to 7, which is in position 5. No, sorry, 8. And 4 points to 3, and position 11 points to position 9. All right. What is going on here? What is going on is that these represent the back pointers. So they're in terms of the positions. So each back pointer is in an array, which we call this the back array, right? And then we could call this array the actual initial array, which I'll call A. Now these could be any kind of numbers like floating point or whatever, but these of course are integers. Now there's another integer here, another integer array, which is maximum subsequence length. So that means that the item in position 4 is the end of a subsequence which has 3 elements, 2, 5, 8. Now, when we look at the maximum length of a subsequence, then this would be the actual answer to the problem if you asked what is the longest strictly increasing subsequence. The answer is 5. Now, of course, if you want to know what that subsequence is, you would follow the back pointers here to 8, This goes to position 5, this goes to position 2, this goes to position 1, and that's the first one there. So that would allow you to recover the actual sequence. Now there's an additional array we need, because we need to build this thing forward. And so this array here that I have will be the position of the end of the largest sequence that ends at that point. All right, so what I'm going to do is I'll delete all these things, most of them, and then we'll build them up. All right, now, initially, we start out with the back pointer. We have pre-processed the first number in the array, number 1, which is 2. And this index here goes all the way down to here. So that means that we're going to have these columns here. I should draw pencil marks here and here, but that would mess up. That would make things look too crowded. The back pointer of this element in position 1 is in position 0, which is the fictitious minus infinity. And the best number of any length is 1. Okay, now let me put in the various length indices here. We have length 1, length 2, length 3, and so forth. So the best of length 1 is the 2. All right, now we're going to draw a horizontal line here, because for the arrays down here, these indices here are the blue indices, and these are the green indices for these two arrays, the initial array and the back array, the back pointers. All right, now, the next thing we do, we process the individual things one at a time. We take 5, and we ask ourselves the question, what's the number that is less than 5, the first number that is less than 5 that I can see? And the answer is 2. 2 is less than 5. So I'm going to write a 5 here, and that gives me an array of size 2. And the index of that 5 is 2. Well, that's perhaps not so obvious what I did, but as we proceed, it will become more clear, I hope. All right, now we're going to look at the third position, which is number 1. Now that number 1 is actually, well, we need a back pointer for this. The back pointer for this is 1. So this is the index of the number that precedes 5. All right, now, we're looking here, and we're looking at this 1, and we observe that both of these numbers are larger than 1. So 1 can't follow either of these numbers. 1 can only follow 0. And so its back pointer would be 0. It can only follow the minus infinity. All right, now that means that the best subsequence of length 1 isn't 2 anymore. It's just plain 1, because we delete a number to replace it by a smaller number which has the same length value. All right, now, the best index of this number, of course, since that number is 1, the best index is 3. All right, now let's proceed with the next number. Notice that there's no third column here, because we haven't yet found a subsequence of length 3. However, the 8, now, when we go to this, we discover that we can slap it on the 5. So we now get a subsequence of length 3, where the third element is 8. And the back pointer is to position 2, which is this 5. All right, now, we're not done. The best index of the best length is now 3, or the best of that length is 8, and the position of the best end of that is 8, and where is it? 8 is in position 4. So you see how I built that up. All right, now let's go to the next one. The next one is a 6. You take this 6 and you compare it to these, and you ask, what's the first number to the left? As I move to the left, what's the first number that's less than 6? The answer is 5. Now, 5, that means that this number is replaced by the 6. Because 6 is a better choice than 8. Because it's smaller and allows more possibilities. We will see later why it was a better choice. So that means the back pointer to 6 is now 5, which is in position 2. And we still don't have anything of length 4, any subsequence of length 4. All right, now when we go to 9, that will give us a new length, won't it? Because the back pointer could either be 8 or 6. But we'll follow the rule that we'll take the smaller choice, meaning the back pointer will always be something that's here in this list. We can call these the live numbers, and the ones that are not there, which are 2 and 8, we could call those dead numbers. No, actually, 2 is there, isn't it? Well, no, they're not really dead. They're going to be eventually used, but they're not in this list of actively looking for partners going to the right. 2 has its partner, which is 5 to the right. All right, now, when we go to 9, we're going to look for a number that is less than 9, and the first number is 6. That gives us a 9, and we have a subsequence of length 4. And the back pointer for 9 is going to be 5 because it's pointing to the 6. All right, now the best, what we have here is the best subsequence of length 4 ends in 9, and 9 is in position 6. That's what that means. 9 is in position 6. All right, now we'll proceed here with the next number, which is a 4. Now 4 is in position 7. In order to get its pointer, I have to go all the way back to this one, which is a 1, which means that the back pointer for 4, which is in position 7, is the number in position 3. Well, that's not going to work very well, but you notice that what happens here is this 5 then is eliminated and replaced by the 4, because that's a better choice for a sequence that has length 2. And then the 4 is in position 7, I then write 7 there. All right, now we're going to proceed. Let's see, 7 has back pointer 6, so that's a 2. No, that's 5. All right, now I want to point out this retroactively, we killed the 8 to replace it with 6, even though they were both equally good as far as 9 is concerned. But they're not equally good as far as 7 is concerned. If we'd left an 8 here, we wouldn't be able to get a subsequence of that length. Now 7, since its back pointer is 6, it replaces the 9. And since 7 is in position 8, we'll update that as well. All right, so now we can see how that works. Every time we put an item into this array here, we replace the one that was there before in that position, where the position refers to the length of the subsequence ending in that number. All right, now, when we get to 3, that's in position 9, we're not able to do very much, if anything. We go back this way, and this is the very first, the rightmost element that is less than 3. Now this means that I'm going to erase this 4 and put in 3. And since 3 is in position 9, I write 9 there. Now the back pointer of 3 is the 1, which is in position 3. All right, now we come to 8. Now you notice I've erased 9. So when I have an 8, I can actually attach it and lengthen the rule. But that was why it was important to replace 9 by 7 in this position. So when I get 8 here, that points to the 7, which is in position 8. So that's the back pointer there is 8, pointing to position 8. And you notice now we get a subsequence. Since this subsequence has length 4, we get an extra length here. It's now length 5. And this particular item is in position 10. All right, now the last thing to look at is the 4 in position 11. Now, when we look at this, we go back to the first thing below it that we can use. The first thing we can find that is less than 4 going this way, and it turns out that's the 3. And so we have to replace the next item by 4. And we have to write 11 here, and let's not forget our back pointer, which is the 4 goes to, what happened to the 3 here? Oh, it goes to here, which is the 9. There we go. All right, so now looking at the monotone sequence, we can then pick this up. The maximum length is 5. So we're going to start in position 10 and follow the back pointers. This says to go to position 8. And then this one says to go to position 5. And this one says to go to position 2. And this one says to go to position 1. Now this is 0, which means we're done. So that means that the maximum length monotone increasing subsequence is 2, 5, 6, 7, 8.